Just making sure. All right, number 2. They tell us that there is a proton launched towards a helium atom, and it stops 5 nanometers away from the helium atom. I want to remind you that this problem sounds notoriously to me like a electric potential energy question, in that we're asked about the velocity and kinetic energy necessary to get one particle close to another particle. So if you don't remember, electric potential energy is Q1, Q2, K over the separation distance, because electric potential is just QK over the separation distance. Now, positivity and negativity, let's hold off on that for just a minute to not confuse you. If I have a helium nucleus with 2 positives and 2 negatives, it has a +2 positive charge, or +2 E charge, where E is the charge on the electron or proton. And I'm trying to fire a proton, which would be +1 E, so that it makes it a distance of 5 nanometers away from the nucleus when coming to rest. Well, look, the electric field from the nucleus is in that direction. So my particle will have to have a velocity in this direction, which will be slowed down until all the kinetic energy is converted into electric potential energy when it reaches the 5 nanometers. So from someplace very far away, it was fired with kinetic energy, and it kept coming closer and closer and closer and closer, slowing down the whole time until it stopped. And then, of course, it would get turned around and pushed away. So this is a conservation of energy question. And the kinetic energy it has here will have to be equal to the electric potential energy it has 5 nanometers away. Does everybody understand that? Any question about that part of this question? Okay, so let's find out how much potential energy it has when it's 5 nanometers away. That would be Q1, Q2, K over R, which is going to be 1 times 10 to the negative, not 1, sorry, 1.6 times 10 to the negative 19th coulombs, the elementary charge, which you have on your equation sheet, times 2 times 1.6 times 10 to the negative 19th, because it's 2 protons in a helium nucleus. Any question about that? Go ahead.
For this problem, I actually looked up like what the charge of a proton was, and it's 1.6 at 10 to the negative 27. So for all the examples...
That's the mass.
Oh. Oh, sorry. Up. Never mind. Okay.
We have to know that helium has 2 protons for the exam.
Ooh, that's a good question. His question is, do you have to know that a helium has 2 protons? I'd have to say no, but to be quite honest with you, I didn't think that through when I was reading through the exam. So if you need that information, I can provide you with a periodic table, or I could probably just tell you.
Like if it was one of the first ones, it's obvious, but if they use anything over like...
Yeah, I'm trying to remember, because I know the AP1 exam has a collision between like a uranium and something else, but they give you the information you need. It's not charged because it's a momentum question, but they give you the mass and stuff. I can't imagine they wouldn't tell you. 9 times 10 to the 9th, and then the separation distance, 5 nanometers, nanos 10 to the negative 9th. They don't have to give you that, the conversion. It's supposed to be on the equation sheet. You're expected to be able to do the conversions off the equation sheet. All right, so that's the answer for how much energy there is. So this would equal the electric potential energy or the kinetic energy. The object has to have this much kinetic energy to just make it to that point and stop, converting all of its kinetic energy into electric potential energy. I don't know what that answer is. It's going to be a relatively small number, though. What's that?
I got
0.86? I don't think it's, I think it's going to be like times 10 to the negative 20th.
Yeah, I got 9.27 times 10 to the negative 20.
9.2 times 10 to the negative 20th joules. Right? I'm just looking at the negative 9 in the denominator and the 9 in the numerator makes positive 18 in the numerator. So I have negative 19, positive 18. That's negative 20. So the numbers, you work those out. But yeah, 9.2 times 10 to the negative 20th looks good. So this is equal to kinetic energy, which is actually the second question, I believe. The first question is how fast it has to be launched. That's you setting this equal to 1/2 mv squared. But you'll need to use the mass of a proton here, which is 1.67 times 10 to the negative 27th kilograms. So, again, you would not have to have that memorized. And that's how you figure out the velocity. It's hella fast. I mean,
10,000.
so, any question about this one? Or any further question about this one? I think the next one's interesting. Look, the later stuff in the exam review is stuff that's more recent, like, you know, circuits and stuff. It's the earlier stuff in the exam review that's older. So, the next one was about the triangle, right? Something like that. That's not a very good rendition of it, but this one's not nearly as hard as it looks. So don't be bowled over by it. One good reason for them to use like a pyramid like this, a triangle-based pyramid, is that all of the lines that connect one charge to the next are all the same length. So a charge is always the same distance away from any other charge. Look at the picture that's in your exam review. You'll notice what I mean. And the reason why this is important is, if you'll remember way back to this topic, it takes no energy to put the first charge there. The amount of energy it takes to bring the next charge is equal to the amount of potential energy there is between them. So this would be Q squared times K over L. That's how much energy must be between them, because it's based on the energy for every two. So if I bring a third one here, that's a distance L away from the other two, well, then I have to add Q squared K over L for this connection and Q squared K over L for this connection. Well, how many pairs of two are there? Look at the picture. I'm pretty sure there's 6 of them, which means that the total amount of energy must be 6 Q squared K over L. There's 6 pairs of 2. Now, you wouldn't be so lucky if it was a square or a cube. Because if it was a square, not that I've seen the exam or anything, but if it was a square, you've got a problem there. You don't have to worry about the energy for the first charge, but if this one's the second charge, and this is the third charge, and this is the fourth charge, well, this might be a little harder, right? So you're going to have the energy between these two, the energy between these two, the energy between these two, and the energy between these two, right? So you're going to have 4 of those, plus the energy between these two, and the energy between these two. 2 of those. They're different distances, though. So you'd have to make sure that you were aware of the different distances. A square makes it harder, a cube makes it harder still. That's why they used a pyramid, because it's not so tough. But remember, all potential energies are interactions between 2 or more objects, so every pair of 2 requires a set of energy. Any questions about that? Okay. Next question, the exam review. All right, so there's my 4 microfarad capacitor, and from A to B, we establish a 12-volt potential difference, and we're going to charge the capacitor up. So the amount of charge stored in the capacitor will be C times V. This equation's on the equation sheet. So 4 times 10 to the negative 6 farads times 12 volts, or 4.8 times 10 to the negative 5th coulombs. Any question about that? How much energy is stored? The energy is 1/2 CV squared. So 1/2 times 4 times 10 to the negative 6th times 140, well, 12 squared, sorry. I don't know. You guys probably give me the number. What is it? Times 10 to the negative 4th joules. All right, so that's it, right? Then it's isolated, and we're going to put a dielectric in the middle of dielectric constant 2. All right, well, the moment I do that, if it's isolated, the first thing that I know that changes by definition will be the capacitance. The capacitance has now gone to 8 times 10 to the negative 6 farads. Right, the dielectric is a scalar value that scales the amount of the capacitance because it scales the dielectric. So what I had before was, epsilon naught A over D, the capacitance of a straight parallel plate capacitor. This changed from epsilon naught to 2 times epsilon naught. So the whole capacitance just doubled. But the potential difference was removed. So the moment I put the dielectric between the plates with the potential difference removed, then the charge has to stay constant because the charges have nowhere to go. So if the charge stayed constant and the potential suddenly doubled, the capacitance suddenly doubled, the potential difference suddenly went in half. So all of a sudden the voltage across that capacitor became 6. Now you don't have to do it that way. You could say, well, Q still is 4.8 times 10 to the negative 5th, but the capacitance is 8 times 10 to the negative 6th times V, and you can do your math and figure out that V has to be 6 volts. Did anything else change? Yeah, the amount of energy changed. Because the voltage is different and the capacitance is different, the amount of energy has changed. Now, you could use a different version of calculating the potential, like Q over V or Q over C, but, it's not a big deal. 12 goes to 6, and the 4 goes to 8, which I think is going to mean that the energy goes down. So it becomes 1.44 times 10 to the negative 4th joules. So it probably pulled the dielectric in since the energy was reduced.
So can we talk about that quickly? So because you just said that energy.
Let's think. Let's make sure I'm saying it right, because I don't want to screw that up because I'm just saying it right off the top of my head. Since there's less energy than there was before, you don't have to do work on the system. The system did work on me. So yeah, I had to pull the dielectric in and reduce the overall energy. If I had to push to put the dielectric in, then I would have been doing work on the capacitor and I would have added energy to the system. So it must have pulled the dielectric out of my hand and putting it in there. Does that make sense? Energy went down. So energy came from the capacitor to pull the dielectric in. Now, the question wants me to redo all of this, but this time, do not throw away the 12 volts. So if I maintain the 12 volts, the capacitance still doubles. But this time it's connected to the potential difference, which means that if the capacitance doubled while connected to the potential difference, it will draw more charge in. The capacitor can hold more now. The voltage was the same, so there's a reservoir of charge available to me. So I will pull charges from that reservoir to meet the demand of a new capacitance. So I would assume that the charge in the capacitor would now double because the capacitance doubled from 4.8 to 9.6 times 10 to the negative fifth. I would also expect that the energy doubled because it was cut in half before, so I would imagine the energy doubled this time. Does that work out? I have to do the math on it, but I think it does. You're going to have new capacitance of 8 times 10 to the negative 6, and the voltage is 12, yeah. So since the capacitance doubled, I'm imagining, what's that going to be, 5.96 times 10 to the negative fourth joules, which meant you would have to push that dielectric in between the plates of the capacitor. Yeah, that's on the exam. I'm sure of it. I'm sure of it. Mostly because I remember writing this question. The first thing you need to realize is that inside our charged shell, the electric field is 0. The electric potential, though, is a constant. And that's related to whatever the charge is on the outer shell. Now, if it's neutral, the potential could be 0 unless there's an external electric field. But if there's no external electric field, then there'd be no, there'd be no imbalance of charges. The electric potential would probably be 0. But I wouldn't count on that. I would count on knowing that the electric potential inside a conductor is a constant and the electric field is 0. We should know that if the whole thing has a net charge of, say, Q, then outside of it, if this has a radius of R, we know the electric field, from 0 to R is 0. And we know the electric potential from 0 to R is a constant. But the electric field for any point that's, greater than R, well, that's going to be, Q, K over R squared, right? It's a inverse square reduction, while the electric potential outside will be Q, K over R. So one tapers off at a greater rate than the other. Look, just so you guys know, it's hard to test that. So they could either ask you for what the electric potential would be at that point, or they're going to ask you to recognize a graph. So I can imagine graphs that look like, that have no labels except for R here. And they don't tell you whether it's electric field or electric potential graph, but they can ask about either. So they'll have something like, stuff like this. Well, obviously one's a kind of a constant. One shows it building up and then tapering off. One shows it decaying, but how do you know whether this is 1 over R or 1 over R squared? If it's just a sketch, it's hard to know. So generally what they will do is they'll put something like that next to it to let you know this is supposed to represent a 1 over R graph, and somewhere else will be one. And we've seen this on the AP exam, so this isn't a surprise. They will tell you, they want you to know specifically, is this one decaying by R or decaying by R squared? And this graph is certainly different than one that would have it right along 0, right? So, everywhere, if they want the electric field inside a conductor, you're going to expect a graph that's 0 all the way to R, and then something happens after you pass R. Now, this question is certainly different than having a say an insulator or conductor on the inside, and then say, some kind of conducting shell on the outside. I mean, if this is positively charged in here, then you have to be aware that it still has an electric field of 0 inside this conducting shell out here. Which means that the electrons are all brought to the inside of the shell in such a way to create an electric field that's 0 outside the shell. So the protons will be, revealed on the outer edges. So the outside of the shell will be positively charged, the inside of the shell will be negatively charged. There is clearly going to be an electric field in here. No electric field inside the shell, but then there'll be an electric field out here. Because our Gaussian surface out here still encloses a net charge of Q, whatever's on that insulator on the inside. So the electric field out in this region would be as if the shell didn't exist. Right? It just has that section where the electric field is going to be 0. Now, we know that there's going to be a question that has some kind of irregularly shaped, conductor. They're going to ask this question probably just to see if they can throw you. The electric field is still 0 inside of it, even if there's a massive electric field on the outside. So if you had some strong electric field out here, the electric field inside the conductor is still 0. Now, if you do have a strong electric field out here, it's going to push the charges around. The charge distribution on this will not be uniform. It wouldn't have been uniform before because it was irregularly shaped. The charges on an irregularly shaped conductor will configure themselves so that the electric field is 0 inside. So they will not be uniformly distributed. That's spheres. But we should expect generally negative charges to move away from the field and positive charges to be on the other side so that the electric field inside is canceled out and we get a net electric field of 0. So that's why we have the positives on this side and the negatives on that side, so that the electric field inside will maintain that 0.